electrophoresis, or CE, is a rapidly developing analytical technique for the separation of water-soluble components from small sample volumes. Capillary electrophoresis was developed by Jorgensen in 1981, building on the pioneering work of others such as Herten and Everarts. It is fast, economical, and has a very high resolution. A typical separation often takes less than 10 minutes, requires only a few milliliters of buffer solution, and is capable of differentiating very similar components within a mixture. Capillary electrophoresis is complementary to other separation techniques, such as high-performance liquid chromatography, HPLC, ion chromatography, and slab gel electrophoresis. The primary benefit of capillary electrophoresis is that the technique offers greater separation efficiencies up to 2 orders of magnitude. Capillary electrophoresis also offers advantages over slab gel electrophoresis in terms of speed, ease of automation, and quantification. Capillary electrophoresis has found a huge range of applications, and new ones are being developed all the time. The technique is already in widespread use, for example in DNA sequencing, the separation of proteins from body fluids, and the detection of low levels of impurities within a drug. But perhaps the most novel application of capillary electrophoresis is the analysis of components in a single living cell. Separations are normally carried out in free solution, with a buffer-filled capillary. With a high voltage applied across the capillary, an electric field is created within the capillary, and the molecules migrate within this field according to their size and charge. A minute volume of sample solution, typically between 1 and 20 nanoliters, is injected into the capillary at the anodic end, and the analytes are detected in the capillary near the cathode. Due to an important feature of capillary electrophoresis called electro-osmotic flow, both positively and negatively charged as well as neutral species can be eluted at the cathodic end of the capillary. In an actual CE apparatus, the 2 buffer-filled reservoirs are connected by a fused silica capillary. The capillary has an internal diameter of 25 and 100 microns and has an outer coating of polyimide to make it more flexible. A high voltage between 5 and 30 kilovolts is applied across the capillary via platinum electrodes immersed in the 2 buffer pots. The detection of analytes is usually achieved by absorption of light seen through a window in the polyimide outer coating of the capillary. A range of commercial instruments is available with auto-samplers at both the inlet and outlet end of the capillary. This not only facilitates injection of the sample, but allows a program of rinses to be carried out between the analyses, ensuring that no residual sample molecules are left sticking to the sides of the capillary. These could easily affect subsequent separations. The principles behind the separation of ionic species by CE are straightforward. Components of a mixture are separated on the basis of their mobilities, which are dependent upon charge and size. Consider a sample containing 2 cations of equal mass, one with a charge of +2, the other with a charge of +1. The double-charged cation will be detected first, as it has greater mobility than the ion with a single positive charge. In a situation in which a sample contains several cations of differing size, but all carrying the same charge of +1, the smallest cation will elute first, due to it having the lowest mobility. Looking at the actual separation of a peptide series, we can see this taking place. The simplest case to consider is that of a series of glycine peptides. If we take 5 peptides, di, tri, tetra, penta, and hexaglycine, and make them up in a buffer solution of around pH 2, the peptides will all be fully protonated, and each will carry a charge of +1. When a voltage is applied across the capillary, they begin to separate. The smallest, diglycine, is the first to elute, with the others following in order of increasing size, with the largest, hexaglycine, passing the detector last. From the electropherogram of this separation, the order of elution is clearly evident. For inorganic cations, the order of elution is again in accordance with their charge and size. An important property of liquids to which electric fields are applied is the induction of electro-osmotic flow, which provides a bulk movement of solvent towards the cathode. With a silica capillary at high pH, deprotonation of the silanol groups on the inner wall of the capillary results in the wall becoming negatively charged along its length. Although some positively charged ions become firmly adsorbed on the capillary wall of them to completely balance the negative charges of the silanol groups. A second layer of cations forms to balance the charges, but unlike those adsorbed to the wall, these ions are free to move. These charged species form an electrical double layer along the entire length of the capillary. During electrophoresis, the non-adsorbed cations in the double layer migrate along the wall towards the cathode, carrying with them the core of liquid. The migration of these excess cations in the double layer results in a plug flow, rather than the parabolic flow of pressure-driven systems, such as that found in HPLC. As electroosmosis produces a flat flow profile, the only source of band broadening is diffusion, and so peak efficiency is maintained. Protonation of the silanol groups increases with decreasing pH. Below about pH 3, the silanol groups are almost fully protonated, so electroosmotic flow is very low. The rate of electroosmotic flow increases with pH, reaching a maximum at about pH 10. At this pH, the liquid is moving down the capillary at over 2 millimeters per second. The bulk flow of solvent due to electroosmosis can result in the elution of both neutral and negatively charged species at the cathode. Cations will migrate ahead of the flow front, and so will elute first. Neutral species will be carried along by the electroosmotic flow and will elute next. Although anions attempt to migrate towards the anode against the electroosmotic flow, in most cases the electroosmotic flow is sufficient to cause a net movement towards the cathode, and so the negatively charged species will eventually be detected. Mobility is the key quantity characterizing each analyte in CE. Electrophoretic mobility is defined as the velocity corrected for the electroosmotic flow in unit potential gradient. In order to be able to calculate the mobility of a particular analyte, it is therefore necessary to know the electroosmotic flow velocity. The easiest way to determine this is to include a neutral marker in with the sample. The mobilities of the various components of the sample mixture can then be determined by using this equation, where mu is the electrophoretic mobility, referred to simply as mobility, L is the length of the capillary up to the detector, T is the time taken for the analyte to reach the detector, T0 is the time at which the neutral marker passes the detector, V is the voltage applied during the separation, and capital L is the total length of the capillary. SI units of mu are meters squared per second per volt. This equation may be rearranged to its more usual form. Capillary electrophoresis is an excellent technique for separating species carrying differing charges, but there is an obvious difficulty in resolving neutral molecules from each other. To overcome this problem, micellar electrokinetic capillary chromatography, or MECC, was developed by Terabi in 1984. Micelles are aggregate structures formed by ionic surfactants, when they are present above a certain critical micelle concentration, or CMC, in an aqueous solution. Each micelle has a hydrophobic core and a charged hydrophilic outer shell. Sodium dodecyl sulfate, or SDS, is a good example of an anionic surfactant and will produce negatively charged micelles above a CMC of approximately 10 millimolar. In MECC, molecules can be separated by virtue of the partitioning of the various components between the aqueous mobile phase and the hydrophobic interior of the micelles present in the electrolyte and forming the pseudo-stationary phase. The more hydrophobic a non-polar molecule, the more time it spends within the micelle. Because electro-osmotic flow is in the direction of the cathode, even though the negatively charged micelles attempt to migrate towards the anode, they generally have a net movement towards the cathode. Consider a mixture composed of two neutral species, A and B. A is hydrophilic and does not enter the micelles at all, while B is more hydrophobic and partitions between the micelles and the aqueous buffer. Because of the difference in partitioning characteristics, these two components can be easily separated by MECC. Having been carried along by the electro-osmotic flow, A is the first to arrive at the detector. B is the next, as its passage has been retarded by its interactions with the micelles. And finally, the micelles themselves will be eluted. This is analogous to countercurrent chromatography. The separation of components due to partitioning between micelles and water can be expressed in terms of the capacity factors of the analytes. The capacity factor K' is the number of moles of analyte in the micelle divided by the number of moles in the water. K' can also be calculated from the migration times of the various components and is given by this equation, where Tr is the migration time of the analyte, T0 is the migration time of the neutral marker, and Tmc is the migration time of the micelle. If K' is equal to 1, then the analyte partitions equally between the two phases. A solute has a capacity factor of 0 if it is only found in the aqueous phase, and an infinite value of K' indicates that the analyte is completely bound to the micelles. MECC is not only used to separate neutral species, but is also useful in the analysis of mixtures of charged and uncharged molecules. Whichever mode of CE is used, it is important to optimize the conditions for the separation. Since the number of variables is small when working in free solution, and the physical principles on which separations are based are well understood, optimization may be planned rationally in free solution capillary electrophoresis. Consider the separation of weak acids, where the degree of ionization is dependent on pH. A good example is this pair of isomeric acids, 3 and 4-methylpyridine. At low pH, both are fully protonated. Having the same charge and being effectively the same size, they have very similar mobilities. Changing to high pH does not help, since at high pH both are uncharged and thus both migrate with the electro-osmotic flow. How then can this pair of acids be separated? The solution is to take advantage of the equilibrium position in the reaction, which is dependent upon pH. A convenient way to express this is graphically, showing the fraction of the base form as a function of pH. Half of the 3-methylpyridine is in the base form at pH 5.68, its pKa value. Since 4-methylpyridine has a higher pKa value, 6.02, by choosing a buffer with a pH midway between the two values, we can maximize the difference in the fraction of the two species in the base form. The electropherograms support this theory. Exactly as predicted, the optimum separation is found by choosing a buffer pH intermediate between the pKa values of the two acids. Optimization of micellar separations can be approached in a similar way. This graph shows the binding curves for two analytes to a micelle. Good separation requires a choice of SDS concentration that ensures the analytes are near their half maximum binding level. As a rule of thumb, an optimum K' value is between 1 and 10. Another important consideration in the optimization of separations is peak shape. For best resolution and peak shape, the concentrations of analytes should be much less than the concentration of ions in the running buffer. This is to ensure that the presence of analyte ions does not distort the electric field characteristics in the capillary. Generally, a 100-fold excess of buffer ions is advisable. For example, with a 0.1 millimolar sample, a 10 millimolar running buffer should be used. Peaks which show tailing occur when the ratio R of the mobility of electrolyte to that of the analyte is greater than 1. Fronting is seen when this ratio is less than 1. A perfectly symmetrical peak is produced when the mobilities of the analyte and the carrier electrolyte are exactly matched. Asymmetrical peaks may lead to poor resolution, as they can mask the peaks of other closely eluting compounds. Since the ideal ratio is unity, the greater the divergence of the ratio from unity, the greater the peak asymmetry. Strictly speaking, it is not injection but introduction of sample to the capillary. Since the capillary must be moved into the sample and out again into the running electrolyte, it is unlike HPLC, which is an online injection technique. However, the term injection is more commonly used to maintain the analogy with HPLC. As CE offers the possibility of both high separation efficiency and short analysis times, it is important to introduce the smallest possible volume of sample. This preserves the important characteristics of this technique. Although there are several methods of sample injection, the two that are most frequently offered on commercial instruments are electrokinetic injection and hydrodynamic injection. Electrokinetic injection involves the direct electromigration of the sample into the capillary following application of a transient high voltage. This technique can be very selective, since the amount of each analyte injected is dependent upon its mobility and the electroosmotic flow. Hydrodynamic injection is achieved through the formation of a small pressure gradient between the inlet and the outlet ends of the capillary. This can be achieved by vacuum, pressure, or siphoning. This method introduces all components of a mixture, regardless of their charge and without bias. Whichever technique is used, automated injection systems give coefficients of variation for the sample that are equivalent to those in HPLC. Concentration of the analytes can be achieved by having a sample solution with a lower conductivity than that of the running buffer. In fact, when using hydrodynamic injection, the sample can be dissolved in pure water. Under these conditions, a disproportionate percentage of the total voltage drop along the capillary occurs across the sample slug, due to its higher resistance relative to that of the running buffer. As the field strength is very high in the sample slug, the analyte ions migrate very rapidly until they reach the leading interface with the running buffer. Larger injection volumes than normal can be used, and analytes can be concentrated, typically up to 10-fold, into a sharply defined band. This effect is known as stacking. The greatest benefits of the extremely efficient separations in CE are obtained if very sensitive methods of detection are available to monitor low concentrations of analytes. A problem of detection is that only very small sample volumes are introduced into the capillary. These result in a detection volume of typically less than 1 nanoliter. With an observation length across the capillary of a mere 50 or 75 microns and a detection zone width of less than 1 millimeter, the problem is obvious. Several detection methods are available to meet these demanding requirements. UV absorbance is by far the most popular method of detection, as it can be applied almost universally. Unlike HPLC, CE can operate at very low wavelengths. This enables the detection of, for example, peptide bonds below 200 nanometers. However, due to the extremely short path length across the capillary, it is only possible to detect concentrations down to 10 to the minus 7 molar. Normally, detection is at a single wavelength, but in some cases, spectral scanning is used. This is particularly valuable for characterization of the components in a complex sample. Fluorescence detection is ideal for compounds that have a strong natural fluorescence. Radiation from a lamp or laser source is focused onto the capillary, and the resulting fluorescence is collected after blocking out reflections and scattering from the excitation beam. Detection limits as low as 10 to the minus 12 molar have been documented for laser-induced fluorescence, but the technique is not as widely used as UV absorbance, since relatively few compounds naturally fluoresce. However, to overcome this problem, a sample may be derivatized to give a fluorescent product, usually before the sample's introduction into the capillary. Alternatively, use can be made of indirect fluorescence. In this method, it is the buffer that contains the fluorophore, with the analytes detected as dips in the background level of fluorescence. An example of an electrochemical method of detection is the Amperometric Technique. This is selective for species that may be readily oxidized, such as the neurotransmitter dopamine. The high sensitivity of amperometric detection, being capable of detecting concentrations down to 10 to the minus 9 molar, make it suitable for measuring dopamine from single neurons. The coupling of mass spectrometry to CE provides mass-selective detection and, ultimately, structural information. Two types of interface have been developed: electrospray ionization, or EI, and one which depends on fast atom bombardment, or FAB, to produce molecular ions. Typical CEMS detection limits are of the order of 10 to the minus 5 molar. Capillary electrophoresis is increasingly used for the separation of protein molecules. However, there is the problem that many proteins adsorb strongly to the walls of the capillary, causing peak broadening and sometimes loss of sample. Protein molecules bind so strongly to the capillary wall, since a protein molecule tends to have many charged sites over its surface. Cationic groups, for instance NH3+, interact strongly and cooperatively with the negatively charged silanol groups on the capillary walls. Various methods can be employed in an attempt to overcome the problem of protein sticking. If a high pH is used, the protein will be negatively charged, and so should not stick to the negatively charged groups on the walls. Alternatively, the use of a low pH buffer would render the capillary walls neutral due to protonation of the silanol groups. Unfortunately, this latter method is not always so effective. Another way is to adjust the ionic strength of the buffer so that there is increased screening between the protein and the charged sites on the wall. Zwitterionic buffers reduce protein adsorption through charge screening almost as effectively as high concentrations of simple salts. The advantage of Zwitter ions over simple salts is that they do not increase the ionic strength of the buffer, thus allowing the use of higher voltages for the separation. A high ionic strength leads to a high current, which in turn produces heat and so causes band broadening. It is possible to derivatize the silanol groups, significantly reducing the negative charge. Such a coating considerably lowers the electroosmotic flow. Other types of coating leave the walls with a net positive charge, which is beneficial particularly for highly basic proteins, such as lysozyme. Several of the commercially available coatings also require a non-ionic surfactant to further reduce protein adsorption. It is also possible to use a dynamic coating, which masks the charged silanol groups but does not remain permanently attached to the walls. A variation on the CE theme uses gel-filled capillaries. These have been developed to facilitate the separation of species such as oligonucleotides and DNA restriction fragments, for which the charge-to-size ratio is the same whatever the chain length. In capillary gel electrophoresis, separation is on the basis of size, using sieving to retard the larger molecules. Capillary gel electrophoresis offers several benefits in comparison with slab gel techniques. The first advantage in the use of capillary tubes for electrophoresis is associated with enhanced heat dissipation. This permits the use of much higher potential gradients than is possible in the slab gel technique, and leads to more efficient separations with a dramatic decrease in analysis time. The second advantage is the ability to directly observe and quantify analytes on the capillary. This removes the need for time-consuming blotting, staining and destaining steps, which are features of the slab gel technique. Capillary electrophoresis already has valuable applications in key industrial sectors, for example, specialty chemicals, pharmaceuticals, biotechnology, the water industry, and food science. Successful separations of inorganic ions, organic molecules, proteins, polynucleotides, and polysaccharides have all been reported. In the water industry, efficient separation and quantitative analysis of common inorganic and organic anions can be completed in under a minute. In drug development, CE assays of new compounds are proving to be robust and cost-effective. In agriculture and food science, CE electropherograms and pattern recognition allow wheat varieties to be identified. In hospital laboratories, CE is being used to screen patients for the metabolites indicative of various serious clinical disorders. All of these applications benefit from the high resolution and high reproducibility of CE separations. What is more, CE offers advantages over other separation techniques in the ease of sample preparation and in the use of small volumes of running buffer. Compared to the use of organic solvents as eluents in HPLC, these aqueous solutions present virtually no hazard in their handling and disposal. Other advantages include ease of method development and low running costs.